Alright, it is 4:38 now, 4:38 p.m. and I find only around 14 of you have joined so far. Okay, but today I shall be discussing some numerical examples on frequency control that I have missed last time. When we were discussing frequency control, we did not consider this or did not solve these numerical examples. So let me solve those problems. Let us uh, see the problems and discuss the issues. Now, is the screen clearly visible to you? Can you see?
Yes, sir.
Okay, so some examples on frequency control. So already we have studied the basic aspects of frequency control, how to model the system, how to analyze the system, and we tried to understand how frequency may be controlled in a power system. Okay, what are the various aspects, right? So now this let us see some of the examples because these examples will help us to understand the problem in a better way. Okay. So first of all, consider this one. Like all together, I shall be one, three, and four problems. Okay, four problems will be discussed. Very simple problems. A 100 MVA synchronous generator operates on full load at a frequency of 50 Hz. Okay, at full load frequency of operation is 50 Hz. The load is suddenly reduced to 50 megawatt. So when the 100 MVA, 100 megawatt basically is the load, frequency is 50 Hz, and then assuming that this was the operating frequency, this was the load. Now the load is suddenly dropped to 50 megawatt. Due to time lag in governor system, the steam valve up begins to be closed after zero point 0.4 seconds. Actually, what happens? Input was corresponding to 100 megawatt, output was also 100 megawatt. Now output reduces to 50 megawatt because of disconnection of load. So what will happen? There will be a change in frequency. This change in frequency will sensed by the governor, and then only the governor can reduce the opening of the steam valve. So that time required for the governor to close the steam valve, the opening of the steam valve was zero point 0.4 seconds. Maybe somebody is trying to join. Let me see. Time was is zero point 0.4 seconds. So during this zero point 0.4 time, what happens? The input remains fixed, output is reduced. So excess power will be there. That excess power obviously will increase the speed of the generator. That increase in speed will be sensed by the governor, and as a result, governor will reduce the opening of the steam valve. So what you have to do here, you have to determine the change in frequency that occurs in this time. So during this zero point 0.4 seconds, this is required for the governor to initiate the closing of the steam valve, reducing the opening of the steam valve. So during this time, how much is the frequency change? This has to be determined. Okay, what is given? It is given that H constant is 5 kilowatt second per kVA. H is the inertia constant. I told you already that. It is popularly the inertia of the generator is represented by H, inertia constant. Okay, and kinetic energy stored is therefore H is given this thing, and what is the H? H kilowatt second per kV of generator capacity. So H represents what? How much is the stored kinetic energy in the generator? The capacity of the generator is 100 megawatt. So what will be the stored kinetic energy at rated speed? It is 5 kilowatt seconds per kVA of generator capacity. So for 100 MVA generator, this will be 5 into 100 10 to the power 3 because it is okay kilowatt seconds per kVA and the load is megawatt 100 megawatts. So like this 5 10 to the power 5 kilowatt second. This is the stored kinetic energy at its speed. That means when the frequency is 50 Hz, stored kinetic energy is 5 10 to the power 5 kilowatt second. Now, what happens? During this zero point 0.4 second, this zero point 0.4 second is needed for the governor to operate say, during this 0.4 second. Therefore, the speed will increase, frequency will increase. So, excess power input to the generator before the steam valve begins to close, it will be 50 megawatt is the difference in power. Excess power is 50 megawatt, and zero point 0.4 second is the time during which this 50 megawatt will be entering, excess power will be entering into the generator. So how much will be the value? It will be 50 into zero point 0.4, that means 20 megawatt second. This much energy will be additional energy that will be stored in the rotor of the generator in the form of kinetic energy. So 20 megawatt seconds means 20,000 kilowatt second. Okay. So rated stored energy is how much? It is 5 10 to the power 5 kilowatt second. Excess energy stored is 20,000 kilowatt second. So what is the total energy stored? It is 50. It is 5 and 1, 2, 3, 4, 5. This much of energy plus 20,000. 20,000. Okay. So this 5 into 10 to the power 5 plus 20,000. This much is the kilowatt second energy stored in the rotor. Okay, and this energy is stored when the frequency is above synchronous. At synchronous frequency, the kinetic energy is how much? It is 5 kilowatt seconds per kVA. That means 5 into 10 to the power 5 kilowatt second. So how much is the frequency therefore? When the this much is the this is the energy stored, because the kinetic energy stored is proportional to the frequency, you can say that the 50 is the operating frequency, and therefore, when this much 5 and 5 to the power 5 plus 20,000, this much is the energy stored, then the frequency will be 50 into square root of 5 10 to the power 5 plus 20,000 divided by 5 10 to the power 5. This much of hertz, that means nearly 51 hertz will be the operating frequency. Okay, so the problem is simple because you have to apply the fact that stored energy is proportional to the square of frequency. Okay, so frequency will be proportional to square of stored kinetic energy. Okay, so that is done here. So is this problem clear to you or not? Whether you could understand, everybody, you see whether you could understand the logic that was applied for solving the problem. See and let me know whether you could understand the problem or not. Or if you have any doubt, you may ask me the question. Any doubt?
No, sir.
Okay. Very simple problem. Obviously, everybody should be able to solve it even before I discuss the problem. Okay. Now, another problem is this is not solved. We can easily solve it. That's why the solution is not given here. Two generators rated 200 megawatt and 400 megawatt are operating in parallel. You have two generators, they are running in parallel, connected to a common bus, and obviously they are supplying power to the load, common load. The group characteristics of their governors are 4% and 5% respectively from no load to full load. Group characteristics of the first generator, 200 megawatt generator is 4%, 400 megawatt generator it is 5%. These are group characteristics. Now, assuming that the generators are operating at 50 hertz and no load, how would a load of 600 megawatt be shared between them? What will be the system frequency at this load? Assume free governor operation. Okay, and then you have to repeat for some other condition when both are having equal group that of 4%. Okay, now let us understand the problem. Two generators rated 200 and 400 megawatt, they are operating parallel and their group characteristics are given 4% and 5%. Now let me, or can you understand what this 4% is? What is the meaning of this 4% group and what is the meaning of this 5% group? Anybody, can you answer what is the meaning of this 4% group for the first generator? Group is 4% for the first generator. For the second generator, it is 5%. Now, what does it mean by the term group? That it is 4% or 5%. What information are you getting from the from this, or what actually you know from this information given in the problem?
Sir, the loss in output voltage?
Huh?
The loss in output voltage?
No, not losing. This is the governor. Governor has nothing to do with the output
Okay,
voltage.
okay.
Governor takes care of the speed. Governor takes care of frequency. Meaning is governor regulation. Governor group means governor regulation. How we define regulation? It is a change in frequency from no load to full load expressed as percentage of the rated frequency. So what is the rated frequency? It is given. It is 50 hertz at no load condition. This is said to be the rated frequencies. Now, group is 4% for the first generator. This means that 4% of 50 hertz. That means 2 hertz is the change in the frequency of the first generator when the load is changed from when the change in the load is equal to the rated capacity. That means when the load change is equal to the full load, no load to full load. Okay. That means if the output is changed from no load to full load, there will be a variation in frequency that is 4% of nominal frequency, 4% of rated frequency. That means there will be a variation of 4% of 50 hertz, that means 2 hertz from no load to full load for the first generator, and 5% of 50 hertz means 2.5 hertz for a load variation of 400 megawatt for the second generator. It is said that the no load frequency is 50 hertz. That means at no load it is 50 hertz, so obviously at full load it will be reduced. So how much will be the reduction in frequency for the first generator? It will be 2 hertz. That means the full load frequency of the first generator will be 48 hertz. Full load frequency of the second generator, 400 megawatt generator, will be equal to 50 hertz minus 2.5 hertz. That means 47.5 hertz. Okay. Now generators are operating at 50 hertz at no load. Okay, this is the operating condition. Now 600 megawatt is the load. How this 600 megawatt will be shared by these two generators? This you have to determine. So can you solve this problem? First question is, can you solve this problem? What the problem statement is actually giving us? First, from the problem statement, we can understand that I have explained that capacity is given, full load, no load frequency, that is also given, and group is given. That means governor groups are given, governor regulations are given. It is 4% for the 5 generator, 4% of 50 hertz means 2 hertz. This means that for a load variation of 200 megawatt for the first generator, frequency variation will be 2 hertz. Means since the no load frequency is 50 hertz, full load frequency will be less than the no load frequency, that will be equal to 40 hertz, 48 hertz. For the second generator, drop will be frequency variation will be 5% from no load to full load. So 5% of 50 hours means 2.5 hours. So there will be a frequency variation of 2.5 hours for a load variation of 400 megawatt. 50 hours is the no load frequency, so 47.5 hours will be the full load frequency for the second generator. Now they are supplying 600 megawatt together. No, they are connected together. Common load is 600 megawatt. You have to determine how this 600 megawatt will be shared by the two generators. Okay. So can you solve this problem? Anybody who can solve this problem? Obviously, the problem is very simple. Can you solve it? So can you suggest the solution? Can you explain it? Bolo. Who can solve it? And if you can solve, can you tell me or can you explain how this can be solved? So one thing you see that here the total load is 600 megawatt and sum of capacity of the two generators also is 600 megawatt. Now when the roofs are 4% and 5%, can you tell me how the load will be shared? Will they, with the first generator, deliver 200 megawatt and second generator deliver 400 megawatt? Will the power output be in this proportion because 600 megawatt is the load, 200 megawatt is the capacity of the first generator, 400 megawatt is the capacity of the second generator. So if you solve it, I think you should be able to solve the problem. Graphically also you can solve, or you can solve it using some mathematical technique also that you can solve, no problem. Okay, so since the groups are not same, obviously sharing of load will not be proportional to their capacity rating. Okay, that means not that it will be not the 600 megawatt will be the, if 600 megawatt is load, first generator will carry 200 megawatt, second generator will be 400 megawatt. This will not be the situation because the groups are not same. In a second case, you have to solve, repeat the problem if both the governors are having 4% truth. So when the groups are same, we'll say that the load sharing will be proportional to their capacities. But when the groups are not same, the load sharing will not be proportional to their capacities. A generator here, this means that since the capacity is 400 megawatt, one of these two generators will be overloaded. One will be delivering power which is excess of its uh,
Rating.
capacity. Okay, but since the generators are operating in parallel, their frequency has to be fixed. So this is will be the basis for solving the problem. When we will be solving the problem, we have to apply the condition that both the generators will have the same operating frequency because generators are operating in parallel. So operating frequency for the two generators cannot be different. It will be same. Okay, it will be same. So what will be that operating frequency? You have to determine when the power output of the first generator is 200 megawatt, second generator it is 400 megawatt, then only the operating frequency will be how much? It will be 48 hours and 57.5 hours. Okay, but now one of the generators should be well loaded. You, therefore, you solve it, but apply the condition that since the generators are operating in parallel, their operating frequency has to be same. It cannot be different for both the generators. So whatever may be the load sharing, their frequency will be common. Same frequency will be the operating frequency for both the generators. So I think because I actually I cannot draw it here now because that facility is not available or I am not that equipped to draw anything here. Okay, but I hope you will be able to solve the problem. All right. So one of you or some of you who can solve the problem will be solving it and sending me the answer, sending me the explanation. Okay. So if it is correct, then I shall send it back to you and send it back to all of you. Okay. So I hope everyone is in position to solve the problem. So solve it and send me the solution. Okay. So I am not solving it now here because I cannot draw it now here. But the problem is very simple. Obviously, what you can do, you can on a common, you can say that common paper, you can draw one axis that is axis for frequency and axis for power. So on the right hand side, you draw it for the one generator. On the left hand side, you draw for the second generator, keeping the frequency axis common, and then draw the droop characteristics. That's different because slope is also given. It is 2.5 hertz for load of 400 megawatt. Another is 2 hertz for a load of 200 megawatt. Okay, and now frequency is common. So if the common frequency is there, now you calculate how much will be the operating frequency and how much will be the load share. So you should be able to solve the problem. You will be solving it and sending me the answers. Then correct answer I shall be sending you back. Okay. Then the third question. A power system has a total load of 1260 megawatt at 60 hertz. Okay, 60 hertz at 60 hertz is the operating frequency, and then the load is 1260 megawatt. The load varies 1.5% for 1% change in frequency. What does it give? Load variation is 1.5% for every 1% change in frequency. That means B is 1.5% for 1% change in frequency. B is given. Okay. What is the meaning of B? It is the how much is the del PD del F change in demand of the load. That means actual load is frequency dependent. Okay. When the frequency varies, actual demand of the load also will vary. How it will vary? It will vary by 1.5%. So load variation will be one per demand variation will be 1.5% of the capacity for 1% change in frequency. So this gives you B. Find the steady state frequency deviation when a 60 megawatt load is suddenly tripped. Now 1260 megawatt was the load. Now 60 megawatt load is disconnected, 60 megawatt load is tripped. You have to find out the steady state frequency. Okay, how much is the deviation? So we will be determining how much will be the falling frequency, how much what will be the new frequency. If there is no speed control, that means no speed control means as if there is no governor associated with the generator. Under this condition, okay, how much will be the frequency variation? So you will be understanding the implication of having a governor with the generator. So when governor is not there, how the system behaves, and if governor is there, how the system performance is improved. From this part, it will be clear. Then the system has a 240 megawatt of spinning reserve. Now a new thing I shall be explaining. Spinning reserve is 240 megawatt, and the governor regulation is 5%. Now the first part, it was said this assume that there is no governor. There is no speed control means there is no governor. And the second part, it is there, governor is there and its group is 5%. Okay. And the system has a 240 megawatt of spinning reserve. Load was 1260 megawatt and the spinning was reserve was 240 megawatt. So you will be utilizing that data to calculate something. Okay. Now let us see. how we can proceed to solve the problem. The 1260 megawatt was the demand at 60 hertz. Okay. Now a load disconnection on 60 megawatt takes place. So remaining load becomes equal to 1200 megawatt. So what is the value of B under this condition? B is given to be 1.5% for every 1% change in frequency. Obviously, this information, this data will apply now on the remaining load because this is the connected load now to the system after disconnection. So 1200 megawatt is the demand now, 12 megawatt is the load now connected to the system. And how much is the value of B? It is 1.5% of this 12 megawatt for 1% variation in frequency. So it is therefore 1.5 into 1200 divided by 100 because it is percentage. Then it is 1% of 60 hertz. So frequency variation is 1% of 60 hertz, right? And load variation is 1.5% of 1200 megawatt. So how much is the value? It is 30 megawatt per hertz. So value of B is 30 megawatt per hertz is the value of B. Load damping or frequency characteristics of load. It is 30 megawatt per hertz. Is this calculation okay? Is it the value of B? How it has been determined? Is it clear to you or not? Bolo. Is it clear to you? Could you understand how B is found out? It is 1.5%. That means load variation. B is 1.5% for 1% change in frequency means demand variation of the existing load will be 1.5% of the existing capacity for 1% change in frequency. So it comes out to be 30 megawatt per hertz. This is the demand. That means for 1 hertz change in frequency, demand will vary by 30 megawatt. Okay. Is it clear to you or not? Bolo. Is it clear?
Yes, yes, sir.
Okay. Now this part. Now so we have found out now first part there is no speed control. If there is no speed control, then what? What happens? Governor will not act. Okay, there is no action of the governor. So input will remain constant what it was before the change in load. Okay, so input will remain constant. So with no speed control, then what will be delta F? Delta F was del PD by B plus 1 upon R. This was the relation. If you remember, del F at steady state was del minus del PD by B plus 1 upon R. Now this R role of R is absent because R is not there, it is not available. If R is not there, it will simply be minus del PD by B. So minus of del PD is the load decreases by 60 megawatt means minus 60 megawatt is the change in demand and B is 30 megawatt per hertz. So delta F will be 2 hertz. That means for a change in load of 60 megawatt only, for a change in demand of 60 megawatt only, frequency will vary by 2 hertz. So you see, what will be the picture of the situation of the system or the performance of the system, how the frequency will vary if the speed control or governor control is not applied. In that case, for 60 megawatt variation in demand, frequency will vary by 2 hertz. So if load decreases by 60 megawatt, frequency will increase by 2 hertz. Okay. So this is the implication. This is the role of speed control. You can understand from here. Now, is it clear to you from this part? Is it clear to you? Because you simply that expression we have applied that del is equal to minus del PD by B plus 1 upon R. This we have derived when we have actually studied the frequency control. Okay. Now is
Yes,
it
sir. Understood.
clear? Could you understand this? Can you understand this first part?
Yes, sir.
The second part, since the second part, what is the problem given? The system has a 240 megawatt of spinning reserve and governor regulation is 5%. Governor regulation is 5%. What does it mean? It means that frequency variation will be 5% of rated frequency. What is the rated frequency? It is 60 hertz. That means frequency variation will be 5% of 60 hertz, means 3 hertz for a variation in demand equal to if the output changes from no load to full load. So now let us find out what is the capacity of the generator, because capacity of the generator has to be known. The parameter is a governor parameter. This is the governor regulation, means parameter of the governor. And this parameter is related with the capacity of the generator. So we must now know the capacity of the generator. We have to know it. How to know it? It is given that load is 1260 megawatt at 60 hour and spinning reserve at that time was 250 megawatt. Now the question is, what does it mean? What is the meaning of spinning reserve? Spinning reserve means reserve that is spinning, reserve that is rotating. That means it means that when the load supply being supplied was 1200 megawatt, then there was a reserve capacity of 240 megawatt available with the generator. Where it was available, this capacity was spinning. That means the generator was synchronized, and the capacity reserve was available to be 240 megawatt. That means the total capacity is 1260 plus 240 means 1500 megawatt. That means the capacity of the generator was 1500 megawatt. Okay, could you understand? Since there is a reduction in system load and an increase in frequency, all generating units will continue to speed regulation, contribute to speed regulation. Okay, the total spinning reserve capacity is equal to the load plus reserve. Spinning capacity is actually the reserve capacity that is rotating, that is spinning. So what is the total capacity? Total capacity is the load 1260 plus reserve, that is 240 megawatt, that means 1500 megawatt. Okay, or we can say that 1500 megawatt is the capacity of the generation in this particular example. Okay, so is it clear how it is 1500 megawatt? What is the meaning of spinning reserve? Whether this is clear, and why the capacity of the generator is found to be 1500 megawatt in this case? Whether this is also clear to you or not? All.
Yes, sir.
Now a regulation of 5%. It means change in frequency causes a 100% change in power generation. But this for 100% change in power generation or 100% change in load, frequency variation is 5%. Okay. So what is R? R is governor regulation. So 1 upon R we can write as this is equal to 1500 is the generation capacity and 5% of 60 hertz is the frequency variation. So 1 upon R is equal to 500 megawatt per hertz. So governor regulation, governor changes the frequency. Governor regulation parameter is actually 1 upon R. We can calculate at 500 megawatt per hertz is the value of 1 upon R, because R is how much? It is 5%. 5% of 60 hertz for change in generation equal to 50 megawatt. Or you can say that 1 upon R equal to 1500 megawatt divided by 5% of 60 hertz means 5500 megawatt per hertz. So what is delta F? Delta F is del PD by B plus 1 upon R. Delta F equal to del PD by B plus 1 upon R. Actually minus sign is there. So the composite system frequency response characteristics is B plus 1 upon R. It is a system frequency characteristics. R is the frequency characteristics of the governor, B is the frequency characteristics of the load, and frequency characteristics of the governor and load together is equal to B plus 1 upon R. That means 500 plus 30 is 530 megawatt per hour. Okay. So what is del F? It is minus del P by this beta B plus 1 upon R. If you put the value 60 megawatt is the change in demand, 550 megawatt is the value of B plus 1 upon R. So So del F is 0.1132 hertz. The change in frequency at steady state after a change in demand of or reduction in demand equal to 60 hertz is only 0.1132 hertz. Now you compare this with the change in frequency in the previous condition, in the previous part where no speed control was applied. That is when there was no governor. So there was no governor. Frequency variation was because of the nature of the load, and now there is governor and frequency variation for it. Both the load and the governor, they are responsible. And previously it was 2 hertz for a demand variation of 60 hertz. So for the same variation in load, now the frequency variation becomes very small, 1.132 hertz. So you can see or you can understand the importance of the governor. Okay, and you understand the importance of the governor. Importance of having governor in the system is actually can be seen from this example. You see that when the governor has no governor, then frequency variation was 2 hertz for only 60 megawatt variation in demand. Now for the same variation in demand, frequency variation becomes very small, 0.1132. So why this is the reduction in frequency variation? Because of the governor. So this is how governor maintains the frequency. Governor regulates the frequency. But obviously, this is free governor mode of operation. Governor is operating on its own only. There is no external, you can say that external control applied through speed changer. That has not been applied. If speed changer is being applied, then in that case, what will be done? This 0.1132 hertz change also will be nullified. This will be brought back to the original frequency. The variation will become 0 hertz if the secondary control is applied. Secondary control is not being applied here. We are discussing about the primary control, that means through governor group, and that governor is reducing the frequency variation from 2 hertz to 0.1132 hertz. Okay, is it clear to you or not? This you see the example, and can you understand the importance of governor in this from this example?
Yes, sir.
All right. Now the last example I shall be discussing here is a small system consists of 4 identical 500 MVA generating units. 4 identical 500 MVA generating units because 4 units are running in parallel. Okay, and all units are identical. Each are having a capacity of 500 MVA and total load is 1020 megawatt. Okay, the inertia constant H of each unit is 5 on 500 MVA base. Obviously, in power system, we all calculate everything on in per unit. So here also we shall be doing that. The inertia constant H of each unit is 5 on 500 MVA base. On a base of 500 MVA, inertia constant is found to be 5. The load varies by 1.5% for 1% change in frequency. That means this is nothing but the value of B. 1.5% for 1% change in frequency. When there is a sudden drop in load by 20 megawatt, then you have to calculate these things. Hmm. A drop in load equal to 20 megawatt takes place, and then you calculate, determine the system block diagram with constants H and B expressed on 2000 MVA base. 4 generators are there. Initially, these parameters are given on a base of generator parameters are generally represented on a base of generator capacity. That means H is on a base of 500 MVA. Okay. Now, if the base is 2000 MVA, total capacity of the 4 generator, now then what will be the uh, uh, value of H and B if you consider 2000 MVA as the base? This is the first part. Second part is find the frequency deviation, assuming that there is no speed governing action. Again, like the first part of the previous example, what will be the frequency variation if there is no governor operation? There is no governor function. Okay. So for this example also we see that 4 units on 1000 MBA base. What? 4 units on 2000 MBA base. What is the value of H? H is 5. Okay. This is 5 is the value of H. Then 500 is the capacity of each unit. All the 4 units are together making a single unit. So what is the total capacity? 500 into 4 means 2000 MBA is the total capacity. On a base of this total MBA, 2000 MBA, then obviously value of H will be 5 again. So this 4 is for the number of units, this 500 is for the capacity of each unit, 2000 is the base, and 5 is the H value. Okay, H is kilowatt second per kVA. That means stored energy by rated stored energy per rated capacity. Okay. Now the base is 2000 MVA. On a base of 500, 5 was the value of H. So if 4 units are there, base total capacity will be 2000. So on a base of 2000, it will be again equal. All right, it's clear. Value of H, how it is calculated, is it clear to you or not? Because those 4 units together as if is now being operating as a single unit, and the capacity of the single unit is obviously equal to the total capacity of the 4 unit, that is equal to 2000 MVA. So on a base of 2000 MVA, what is the value of B? It is 5 obviously, because each having capacity of 500 on a base of 500 MVA was equal to 5. Now on a base of 400 MVA, on a base of 2000 MVA, all these 4 units, their total capacity is 2000 MVA. So obviously it will be equal to 5. Then B is given also. What is 1.5% for a change in frequency of 1%? Now, expressing B on remaining load, 1000 megawatt, 20 megawatt was the initial load. Now, there is a drop of load by 220 megawatts. So, remaining load is 1000 megawatt. And 1000 megawatt on a base of 2000 MVA is zero point 0.5 per unit. Okay. So B is now 1.5% of the load for 1% change in frequency. That means 1.5% of 1000 by 2000. This much per unit. Or this, that means 1000 by 2000, 1.5%. That is 0.75% for 1% change in frequency. That is equal to 0.75 is there in percent. You can express in per unit. So 0.75 per unit megawatt per unit hertz. Okay, so or you can say that it is 0.75% for 1% change in frequency means it is 0.75 per unit megawatt per unit hertz. Okay, so this is the value of B. So with value of B obtained here, H obtained here, you complete the part A. Value of H and B you have to calculate on a base of 2000. Second part is find the frequency deviation assuming that there is no speed governing action. There is no speed governing action means R is not available. Okay, and del F will be del PD by R. Sorry, del PD by B plus 1 upon R. R is not there, it is absent. So del F will be equal to del PD by D. Okay, so with no governor action, del PGS equal to 0. Because why del PGS equal to 0? Because if no governor is there, who will change the uh, opening of the steam valve? So generation also will not change. That's why del PGS equal to 0. System block diagram. You can now draw Kp by 1 plus STP. Okay, so you can calculate it. You can draw it. Whatever was done. Now you can simply put the values and block diagram you can draw. What is Kp? Kp is 1 upon B. B already we have calculated, so it is 0.75 per unit megawatt per hour. So Kp is 1 upon 0.75 per unit megawatt per hour, or it is 1.3 per unit hertz per unit megawatt. and Tp is time constant of the power system is 2h by Bf0. 2h. 2 is already clear. H is 5. B is this value we have calculated. Okay, 0.75 per unit megawatt per unit hertz. Okay, and F0 is the nominal frequency. Means 1 per unit frequency. Fifth charge is the 1 per unit frequency. So this ultimately becomes 13.33 seconds. Okay, 2h by Bf0, put the values, it becomes 13.33 seconds. And del PD is 20 megawatt. So minus 20 megawatt load decreases. So minus 20 by 2000 means minus 0.1 per unit. This much is the load variation. So demand varies by minus 0.01 per unit. So del PD S is minus 0.01 by S. So del FS is will be equal to how much it is? You see that del PD, del PDS, then it is 1.33 is TP, 1.33 is KP, KP by 1 plus STP, KP by 1 plus S time TP. TP is found out 13.66. So from the block diagram, we calculate what is del FS and what is del FT. Del FT is 0.0133 minus 0.0133 it gives minus 0.075t. So these things you can do very easily, no problem. Okay, so only thing is that to understand the meaning of the different information given in the problem and then to apply it properly. Okay, so these are the four problems. These four problems I whole think will help you in understanding the frequency control problem and frequency control mechanism in power system in a better way. Now, if you are having any question, you may ask me. Well,
না স্যার এমনি কিছু নেই এখন
ঠিক
আপনি
আছে।
কি এটা পাঠিয়ে দেবেন
হ্যাঁ হ্যাঁ আমি এটা পাঠিয়ে দেবো and if you are having any other question on whatever I have got so far because today otherwise will be the last class of this session and if you find that anything again has to be discussed you may then call me or you may send me mail then I shall arrange more classes or more class as you want. Okay, if you want to know some clarify something today that you can ask me, I can discuss those things also. Bolo. Or if you have no other question then I shall be finishing today's session.
নো স্যার লাগছে না কারোর কিছু আছে এখন
হ্যাঁ তাহলে তোমাদের কারো কোনো প্রশ্ন যদি থাকে কারো কোনো যদি মনে করো কিছু ডিসকাস করতে